Good afternoon, everyone. Today's speaker is Daniela Černá, who is maybe the unique PhD student at Gold, who is not a PhD student at FIT. She's my student, and she will tell us something about shattering triples in permutations. Daniela, please.
Thank you for the introduction, and thank you all for coming. It's a joint work with Alexander, sitting there, Bartek, and Jan Volec. And first, I would like to start with the definition, so you all know what I am talking about, and we are all on the same page. After that, I would like to take a step aside to talk about flag algebras. So I will show you a proof of Mandel's theorem using flag algebras, and then show you the analogies in our proof for the upper bound. After that, I would like to talk about the lower bound, including the results for small orders, and later the lower bound for the limit. And in the end, I would like to conclude and also mention some open problems. So first, by the symbol, I will just mean the set of integers 1 to n. Permutation is then a bijection, and therefore uniquely determined by this n-tuple. It will mean just the second row of the two-row notation. Do not confuse this with the cyclic notation. By Sn, I will mean the family of all permutations of the same order, n. And now, if you give me a k-tuple A, which is just A1, A2, AK, all numbers from 1 to n, where I can suppose that they are ordered in this way, then the n permutation from Sn, then the pattern in this permutation induced by this k-tuple is a permutation of order k such that these inequalities hold. I have example right away. So if I take the permutation of order 5, defined by this 5-tuple, and A being a triple of 2, 4, and 5, then I can write down these numbers, which will be 3, 5, and 4. It's just the second, fourth, and fifth number. And to get the pattern out of this, I just look at the position of the smallest number in here, and at this position I will write 1. Then I look at the position of the second smallest, and I write 2 at this position, etc. So the pattern will be 1, 3, and 2. Should I wait? Okay. So if you know what the pattern is, I can tell you what shattering is. And if we have a family of permutations, then we say that this family shatters k-tuple A. If I look at the permutations from the family 1 by 1, I look at the patterns that are induced in the permutation by this k-tuple, and eventually I want to find all possible permutations of order k, which is here. If you look at the definition, it is clear that if the size of this family is less than the size of Sk, I cannot shatter anything because I do not have enough permutations to generate all possible permutations. Again, I have example right here. I have chosen 6 permutations, which are written in here. And you can check that these 6 permutations will shatter the triple 1, 2, and 3, because the permutations were chosen in such a way that the first 3 positions actually contains all different permutations of order 3. Also, it cannot shatter any triple that contains 4, because if you take 4, in the pattern there will be 3 in the last position always. So I cannot shatter anything. Looking at this definition, there are kind of 2 possible questions you might ask. One question is that if you fix n and k, what is the size of smallest family S that shatters everything? Which is interesting question in its own. But we looked at the different question, and that is if we fix not only n and k, but also fix the size of s being smallest possible, which is k factorial. What is the maximum number of k tuples that you can shatter, which is part of this definition. So for a family S, we define fks to be just the number of k tuples that are shattered. And then we look at, for k and n, we look at the maximum possible numbers of k tuples shattered, where we set the size of s being k factorial. And small f k n is just the normalized version of this number, because you look at the number of k tuples that are shattered and divided by the number of all k tuples. So this number is always between 0 and 1. It is clear from this definition that it is 1 if you take n being k, because then your family S will be just sk, and you shatter the 1 triple that is in there. Levenstein also showed that even n being k plus 1, you can still shatter everything. Another interesting property of this is that it is monotone, especially it is non-increasing. And I can prove it to you, because you can take S being the family that attains the maximum on n plus 1. And then for each I index or number from the ground set, you can delete the ith position in each of the permutations and look at the pattern that are in use in here. So doing this for each I, you will get permutation on n. And especially this will mean that it shatters at most fkn k tuples. And now you can do double counting, where the number of k tuples that are shattered by S can be counted as I will look for each I at the number of k tuples not containing I that are shattered by S, which is the same as the number of k tuples that are shattered by Si hat. And each k tuple will be then counted n plus 1 minus k times, because it does not contain exactly this many i's. That's why there is this coefficient. I can upper bound this by fkn and then just sum it up. And now I can divide both sides by n plus 1 choose k to get the small fkn plus 1. And this coefficient divided by n plus 1 choose k will give me exactly 1 over n choose k, which is what we need to get fkn. Okay, so it is monotone and also a number between 0 and 1. So if we want to look at the limit n goes to infinity, it will exist. And now we looked at the case k being 3. So we are actually shattering triples with 6 permutations, as was said in the title. And what was known, Johnson and Wickes showed that every 5 is 4/5, and also proved that for all n at least 10, every n lies between these two numbers. There's still quite a big gap, which we wanted to redeem. So we looked at the values every n for small n's. So we were able to find the values for numbers from 6 to 10. 9, my bad. And also we found lower and upper bound. So the upper bound was found using flat algebras, and it's interesting in the limit. But also the values for small n will give me actually upper bound for all bigger n's. So I can also find the upper bound this way. And then the lower bound was found using a theorem from Johnson and Wickes and finding actually good enough family of permutation that shatters enough. So I will walk you through all of this, hopefully. And I would like to start with this result. And to do that, I will take the step aside and show you something about the flat algebras. So forget about the permutations for now, and suppose we have a fixed graph. In the end, I would like to take instead of one graph the sequence of graphs where the number of vertices will go to infinity somehow. But suppose now we have a fixed graph. Then by this symbol, I just mean the density of edges, and it also is the same as the probability that choosing two vertices in the graphs uniformly at random and taking the induced graph on these vertices, I will see this symbol or graph isomorphic to this symbol, which is what I do for bigger graphs. So for example, this just means the density of triangles. And now if I want to count the density of edges in the graph, I can actually first look at the density of graphs on free vertices and then look at the density of edges in these, which gives me this identity. So if I want to calculate the density of edges, I can take the density of triangles multiplied by 1 because I have 3 edges out of 3. Then cherry multiplied by 2/3 because I have only 2 out of 3 edges. 1/3 times density of cocherys, and 0 times the independent graph on free vertices. I can do this also for a fixed vertex. So by this symbol, I will mean that I have a fixed vertex, and I am asking about the probability that if I choose some other vertex from the graph uniformly at random, I will see this graph. So it's exactly the number of neighbors of the vertex divided by the number of vertices minus 1. Similarly for the bigger graphs. And having this, I can average this by choosing the vertex V that I want to fix uniformly at random also. So for example, for this one, the sum will be just the density of edges. For cherry, where the chosen graph is in the middle, I will have 1/3 because out of every cherry, I need to pick exactly this one vertex. Hopefully this is clear. Next, what we want to do is also define multiplication on these structures. And I will not do this in general, but I will do this for these two symbols. And I would like this to be kind of the density of this squared, which can be thought of instead of choosing the fixed vertex and uniformly at random some other and looking if I have found this and doing this 2 times, I can actually choose 2 vertices and look if then choosing one of these will generate the first one and the second will generate the second one. So it will be the probability of cherry with the middle vertex being V and the density of the triangle with one vertex chosen as V. And there's this little O1 because if I do the process by picking one vertex, looking whether it is this graph, and then picking another vertex, looking at it, it might happen that I will pick one vertex twice. But as I said, I would like to go to take the sequence where the number of vertices will go to infinity. So in the end, this probability is pretty small. That's why there is this little O1. And it's supposed to be everywhere later on the slide, and I just didn't write it. And what flag algebras do, they actually find correct what you need to write in these brackets as a square or sum of squares. So it will always be non-negative, regardless of what the density actually is. And if you rewrite it using the multiplication, you will get, for example, this one. So I have minus 1 minus 4 times the edge with one rooted vertex plus 4 times this, plus little o1, which I didn't write. This works for all vertices, so I can average this. So it will still be non-negative, and here I have just the sum of the expression above. And summing this, 1 will still be 1. 4 times this density will be just 4 times density of edges. This will give me coefficients 1/3, and this will give me coefficient 1, so it's still 4 times. And now I have written you again the equation for the density of edges, for which I will want to take this one and substitute it in here to get rid of the density of cherries. And if I do it, I will get this expression. And this part will always be negative because density is non-negative. So I can forget about it to get this inequality. Plus little o1. And now the Mantel's theorem says that if I have no triangle, so this will be 0 because density of triangles will be 0, I will have the density of edges is at most 1/2 plus the little o1 I haven't written. So we wanted to do something similar for our case with the permutations. Or are there any questions to that? Okay. We wanted to do something similar for the permutations. So now our density will be something like this. So for a permutation and pattern, we will look at the number of triples that induce the pattern in the permutation and divide it by all possible triples. Of course, we don't want to do it with only one permutation because we have 6 permutations. And there's a little hack I didn't tell you so far. And the hack is if I look only at the number of triples that are shattered, not looking at the structure, then the permutation P1, P2, P3, P4, P5, P6 shatters same number of triples as identity P2, P1 inverse, P3, P1 inverse, etc. up to P6, P1 inverse. So instead of looking at 6 permutations, I can look at 5 permutations and ask to see all the patterns except the identity. Is everything okay?
Somewhat. Yeah, it's fine.
Okay.
So you're not looking at the camera anymore.
So using this hack, we actually define this for 5 tuples of permutation. And it will just mean I will look at the triples that induce the first pattern in the first permutation, second pattern in the second permutation, etc. And it's still divided by n choose 3. So using this, now our sets will be all 5 tuples of permutations of order 2 and all 5 tuples of permutations of order 3. And now what we want to actually see, if we want to calculate the shattering, is we want to see all possible 5 tuples of permutation that contains each one is different permutation from SE minus identity. So we have 120 different patterns we can see and we want. For any permutation of, or 5-tuple of permutations, the density, if I sum over all possible patterns I can see, the densities of this pattern, I have 1, because I cannot see anything else. And the normalized number of shattered triples is exactly the sum over the patterns we want to see, which is the ones from H. Again, I can do this also with, similar to choosing one vertex V from the graph and having the edge with this vertex. I can color one of the positions in the permutation and define the multiplication. So if I have 2 permutations of order 2 that have 1 position colored, and permutations of order 3 that has 1 position colored, I can define these 2 sets, which is exactly by choosing the colored one and one of the others, and looking whether it induced the first permutation with the coloring, and looking if the other one induced the second permutation in the coloring. And then the coefficient I want to see is 1/2 the sum of the characteristic functions of these events. So all of these coefficients will be either 0, 1/2, or 1. And also they are quite easy to calculate using computer. Of course, this should then be generalized for 5 tuples instead of 1. So I will just again look at the patterns one by one. I have example right here. So if I take the permutation by being identity with the second position colored, then the set 1, 2 induced 1 with 2 colors, 2 colored, and 2, 3 will induce 1 colored and 2, because I cross out the first number, so the colored 2 will become the first one. So this coefficient will be 1/2. And we need these coefficients to define the multiplication, which is just sum over all permutations with one vertex, one position color of order 3, with this coefficient multiplied by the permutation. This can be then linearly extended to linear combinations of permutations by just taking the sum out. And also, again, we need something like the averaging argument. Now, instead of the sum, I will write these brackets. And it just means, in this case of permutations, it just means I forget about the coloring and multiply it by 1/4. And having this, I can show you the results. And now you almost are able to verify it. So there are pattern density expressions. We know exactly what these are, but I did not write them on the slide. That's why you can almost verify it. But regardless what the expression actually are, this matrix is positive definite. So regardless of what these vectors are, the number in the bracket is something non-negative, and after averaging, it will still be non-negative. So we have that this is non-negative, and also going through the coefficients I have told you during the multiplication and everything, you can find that this is equal to the sum of all 5 tuples of permutations of order 3 with the coefficients beta f, where beta f is -1 for every f we want to see, and something between -1/4 and 1 for every other one. And so I have something that is non-negative, and it is equal to minus sum of h from h, which are the patterns I want to see, and plus beta f times f from the rest, and beta f is at most 1. And now I just use the equation I have told you at the beginning, that the sum, if you forget about these beta f's and put 1 in here, the sum will be 1. So this is 1 minus this sum, which will give me exactly this, which tells me that this sum is at most 1/2, and this sum is equal to the value f3 n. Again, there's the little O1s in here, so this works for the limit and goes to infinity. And here is the little big O1 over n, which can be found again going through the proof. So hopefully you believe me that we found the upper bound, at least for the limit. And now we can look at the lower bound and for the results for small orders, if there are no questions to the previous part. Great. So these are the results for small n. Forget the third column for now. I will return to it later. But as I said, f3 is trivial 1. Levenstein showed that it is 1 also for n being 4. And this result is from Johnson and Wickes. And we found these just using computer search up to n being 8. And after that, we actually looked at the double counting argument I showed you in the proof of monotonicity. And we found out that if we want to get here 58 or 60, the permutations as I had, which are obtained by deleting one of the position, will have to shatter at least a 39 in here. So we looked at the permutations that shattered permutations of order 8 that shattered 39 or 40 triples and tried to extend them to find out that none of these can be extended to get 57.
58.
Yeah, sorry. Yeah, 58 and we got 57 quite a lot of times. Thank you. So now we wanted to look at the lower bound for the limit. And it's actually this theorem from Johnson and Wickes, which says that if I have a family shattering alpha and choose k tuples, then for all n, at least n, I can find this. And in our case, it's much nicer because if we set k being 3, these two will kind of cross out to get just n minus 2 over n plus 1, which is how we got the third column in here and is the lower bound for the limit. You can see that although these numbers are non-increasing, these are not. And also it's not still the number I promised you. The number I have promised you was actually found by Bartek, who looked at bigger permutations, and he found this. This is a family of 6 permutations. The first one is identity. Each of them has order 26. And this six-tuple shatters 1,446 out of 2,600 triples, which will give us F3 being at least 0.556. And also the limit using the theorem on the previous slide will give you 0.494. Yeah. Also, these numbers give you actually upper bound for all the next numbers because of the monotonicity. So although our upper bound was 1/2 plus O 1 over n, here you have actually also numbers that can be used as upper bound. So just to sum it up, we were able to show that F3n lies between these two bounds, which are pretty close. We strongly believe that for the limit, the value 1/2 is correct, but we were not able to prove it so far. And we will need to find some other way to actually construct the limit permutations, because we don't think that the blow up, which was used in the theorem, will actually work. So what are the open problems? The bound can still be improved. You can also find the values of f3n for smaller n's. And also all of this can be done for bigger case, which might be interesting, but in this case, you will have to look at k factorial permutations. So the problem gets tricky quite quickly. Thank you for the attention. And here, there are just the results I mentioned.
Okay. It's time for me. Are there any on-site or online questions?
So, can anything be said about these terms, these mysterious terms that you use in the matrix?
Oh, those terms.
These pattern density expressions.
This one? A1 up to A5? Yeah, Honza has them. He sent them to me. It's like each of these is a sum of 6, I think.
So do you want an honest answer? Finding sum of squares is basically doing semi-definite programming in general, and in particular in this part. So you run this semi-definite program with 7,000 watt number of variables. It spits out 64 times 64 positive semi-definite matrix, out of which this 5 times 5 block is the crucial one. And those A1 up to A5 are a result of this optimization.
Okay.
Which they kind of scream at you if you look at this particular solution from the right angle. It should also tell you through complementary slackness, sort of the message how the extremal example, which we don't know how to construct, this example witnessing one half. I mean, it gives you some constraints on them, so because of complementary slackness. So there should be some reasoning, but if we find the particle combinatorial explanation for this particular one, A1 up to A5, most likely you'll finally understand what is the construction we are still missing. It's sort of a bizarre situation where we have a proof for every, and we are missing a construction. But for instance, again, going to the analogy for the proof of Mantel, sort of the analog of A1 up to A5 in that proof would be just A1. It would be just 1 times 1 positive. It would be basically telling you should take a half regular graph. It would be like the analog of this A1 would be edge density minus degree minus non-degree of a vertex. And it would sort of be like, again, this complementary slackness would be telling you, oh, for the graphs that maximize number of edges without triangles, look at a half regular triangle free graphs, which of course is the complete bipartite graph. The guy you wanna put into him.
Thank you.
Yeah, if you are a proof verifier, you kind of don't care. I mean, it's something that the proof works. That's maybe curse, but also the beauty of this technique. Like once you have the matrix, even if the semi-definite programming solver or Jan's coding was rubbish, you can still verify that the proof works, regardless of how many bugs I have.
So maybe another question. So you said that you don't know the limit for n going to infinity, but in the upper bound you claim like 1/2 plus some over 1 over n. Yes. Clearly, if I take the limit, then this 1 over n is 0, right? So is there anything like hidden, or is this some kind of?
Well, we have lower bound and upper bound for the limit, and we don't know.
That you don't know the lower bound for the limit.
No. Maybe I said it, and
we do know lower bound, we do know upper bound, they don't match. In principle, who knows what's the answer? Although we strongly believe we know what's the answer. The answer should be 1/2. But maybe our intuition is wrong. Maybe it's 4.999%. That's still okay.
Sorry if I said it and it wasn't clear.
So the upper bound is clearly 1 or 2.
Yes, the upper bound is 1/2, but the lower bound is something that is still not the 1/2 we want.
Okay, if there are no more questions and no online questions,
No online.
okay, then thank you, Daniela.